Okay, so we've been talking about chemical equilibrium, and last time we talked a little bit about Le Chatelier's principle, and what does Le Chatelier's principle state?
Whenever you make a change, the reaction is going to react in such a way to cancel the alteration made.
You're on the right track. Go ahead, Jason.
If a perturbation in the system increases like it disrupts equilibrium on one side or the other, the reaction will follow forward or reverse to equal out the substances to make sure that they're in equilibrium.
Definitely on the right track. So you have a system at equilibrium, and you do something to disrupt equilibrium conditions, whether it be add a substance, take away a substance, alter the temperature, alter the pressure, alter the volume, etc. The system will respond in such a way to at least partially undo what you have done. One thing I will say, the Pogel packet you took the other day is spot on. I would definitely do that over the weekend to make sure that you have mastery of that concept. I have completed mine, and I will make every effort to post mine today. I would highly recommend that, as well as some textbook problems, just to get a good flow there. And many of you, or most of you, felt comfortable with Le Chatelier's principle the other day. The one aspect that wasn't in your notes that I inserted in your notes now, I can repost, and I just gave you out that half-sheet handout. It's more of a graphical interpretation, and I did see on one practice exam a question that required you to interpret one of these graphs, so it's something I would like to show you. I also, the top one actually is in your AP review packet. I usually don't have you download that until we're getting close to really putting all the pieces together. But that review packet is already on Edline in the AP review tab. So you may want to take a look at it. And I got this from somewhere, and I realized that whoever posted it didn't know how to spell equilibrium, because we know that a U comes after Q, but that's okay. So what we're looking at here is the equilibrium reaction showing the decomposition of hydrogen iodide and then the reformation. So we have a system at equilibrium, and then what happens is, and that arrow in there is a little bit misleading. What happens here is that you add hydrogen gas to a system in equilibrium. I don't really like the down arrow. I think that's a little bit misleading. So when you add equilibrium, that's hysterical. When you add hydrogen gas, equilibrium will shift in the reverse direction, or you can say the reaction will shift in the reverse direction. And now what happens to the amounts of hydrogen gas and iodine? They will decrease. Keep in mind, hydrogen initially increased, so the decrease isn't as much as the increase. And when you shift in the reverse direction, what happens to the amount of hydrogen iodide? It increases. So that's shown graphically here. Here you've got an equilibrium state where Q and K are equal. And what I love about that Pogel packet is that it really delved into Q more. We'll be touching upon Q a little bit more today. Now you add, hence the vertical line right here, the hydrogen gas. Now you're starting to utilize it here, so the amount decreases. A new equilibrium is established, but again, you didn't use it all. The hydrogen iodide amount is increasing under these non-equilibrium conditions until equilibrium is reestablished, and with the reverse shift, you can see the decrease in iodine amount. So this just shows it graphically, and you can get which of the following graphs best illustrates the following. So I wanted to make sure that you at least had seen it previously, although I do feel very confident that you would have gotten it right already, because you are crazy smart. Crazy may not be the best word to use. All right. equilibrium reaction between ammonia and its element counterparts. And a lot of you on the previous quiz missed that question where I asked about formation of a substance. Keep in mind when you're illustrating formation of a substance, you've got to use the elemental pieces. That was in the Pogel packet last time, and you either didn't do it or you missed it. So everything's assigned for a reason. I really tried very hard to give you every single piece in class, but there's just so many concepts, it becomes impossible. What you can see here is in this reaction, you've got an equilibrium reaction, and what's going to be illustrated in both panels here, this one I like because it shows it more at the molecular level, is you're adding hydrogen. When you add hydrogen, you're going to get a shift now. In which direction? If you add hydrogen, equilibrium shifts in the forward direction in an effort to utilize the hydrogen gas you added. You see the vertical, you see the decrease here with the shift because now it's getting utilized until equilibrium is reestablished. You're generating ammonia, you can see the increase, the decrease here. What I like better about this graph is it really illustrates the stoichiometric ratios better, where you've got a 1 to 2 to 3 mole ratio. Okay? So I just wanted to take a minute to go back with that. And hopefully you did some problems in your textbook on Le Chatelier's principle, really understanding it. And if you haven't, definitely over the weekend, get a good grip on this. I know a lot of you think you remember all of it, but you don't, and for many it is new. These are the learning objectives that we wanted to hit here, and I feel very confident that we did. What we are going to pick up with today is illustrative equilibrium calculations. Now this used to be a very, very, very math-based hardcore section. We're really going to simplify it this year. There is one little piece that you won't see on the AP exam. I'd like to show it to you because I think you'll need it for college, and it also shows you some functionality of your calculator that you probably didn't realize that you have. For those of you with the Inspires, I'll probably need a little bit of help because I've never used one of those, to be honest. All right, with these types of calculations, this is going to set the framework up for this chapter, the next chapter, and the chapter after that. There's a certain approach that we do here, okay? Some people like to teach this in honors. I know down at River they do. I think it's a lot for honors, although you guys would have been able to handle it. But you will be very, very good at this with some practice. And we're going to do a lot of problems today. The goal is to be done by 2 with just 45 minutes of Pogel practice, problem practice, etc. And that will make some of you very happy as you look like it's 7th hour on Friday. All right. It does say if volume of gases and reactants and products are the same, you don't have to include volume in your calculations. You can do the whole problem in moles. And when we get there, I'll illustrate that a little more clearly, or a lot more clearly. So here's our approach. It's called RICE. We're going to make RICE tables. And RICE stands for R for reaction. That's your equilibrium reaction. I for initial concentrations, either in molarity or moles, most commonly as molarity. Initial amounts typically are given. Initial amounts will determine whether the forward or reverse reaction is favored. C for changes. These are the changes that the system undergoes to establish equilibrium conditions, molarity or moles, whatever the unit initially you're going to have to carry through. And then finally, E for equilibrium concentrations. Again, molar or moles. We're going to use this approach for each of the following problems we're going to solve. And it looks like there are a whole lot, but we're going to keep it very simple. And again, some practice goes a long way to understanding this concept. Okay, in the first example, it says begin with 1 mole each of phosphorus trichloride and chlorine gas in a 1 liter flask. Begin with. Those are initial amounts. We've got to read critically here. The volume's 1 liter, so the molarity of each is 1.00 molar. Piece of cake. When equilibrium is established at 250 degrees Celsius in the reaction shown, phosphorus trichloride plus chlorine gas yielding phosphorus pentachloride. The amount of phosphorus pentachloride present is 0.8 moles. Calculate, that should be a period, not a question mark. Calculate the value of Kc for this reaction. Okay. What you really need to be careful with is at first glance it looks like they're just giving you all the concentrations and ooh, let's write our Kc expression, plug in and solve. No. Be very, very careful. I am going to rewrite what's on your page. I did it color-coded in that regard for a reason, and that will be made clear. Unfortunately, I bought college-ruled notebooks. I probably didn't pay attention. I'll try and write bigger, but for those of you sitting in the back, you may want to move forward. And there's so many kids in here that we don't have to worry about that today. So here's our approach. R, I, C, E. Equation, phosphorus, trichloride, gas, chlorine, gas, initially we have 1 molar, and the equilibrium amount of phosphorus pentachloride is 0.82 moles in a 1 liter flask. So this, and I can keep it going in red, is 0.82 molar. All of that information was given. They want us to calculate Kc, and we know how to write a Kc expression because we've been through this all week, and I'm sure your homework is completed through what you could do for today. So we should just plug in all those numbers, right? You better not. That would be awful. The concentrations that go here are equilibrium concentrations. Q's come from initial amounts or non-standard equilibrium conditions, or non-equilibrium conditions, I guess is stated more clearly. Initially, you didn't have any of this. And the fact that you don't have any of this tells you you initially must be going in the forward direction. E is equal to I plus C. There's two ways to approach this. I like to get right to X's because I think it's going to make the next piece easier. Clearly you have to go forward. So you're going to be taking away from here, and you subtract 1x because of the coefficient of 1. If you had had a 2 there, you'd subtract 2x. Same thing here. And here you're going to be gaining. So you have plus x. So in this particular problem then, what's x equal to? 0.82, right? Okay, so this is 1 minus x, or what?
1 minus 0.82.
Which is? What? 0.18? Is that what you said? Now you have equilibrium amounts and you're ready to rumble. And I'm just going to square these since they're the same. Easy peasy? The rice approach. Let's take another one. The next one says a 1 kilogram sample antimony 3 sulfide and 10 grams of hydrogen gas are allowed to react in a 25-liter container at 713 Kelvin. At equilibrium, 72.6 grams of hydrogen sulfide gas is present, and we want to know the value of Kp at 713 Kelvin. Okay, let's see what we've got.
Can you, no, can you say that? Kp equals Kc?
Why?
Because it's the same number of moles of gas in the products and
Yes,
reactants.
the delta N of the gas is 0. Absolutely. All right. So the mass of that solid is 1 kilogram. The mass of hydrogen gas is 10 grams. The volume is 25 liters. Temperature given as well. So this is where you are initially. Then at equilibrium, the mass of hydrogen sulfide gas is 72.6 grams. We want to know Kp. Also at 713 Kelvin. So we're going to again use a rice approach. And again, we don't include solids or liquids in equilibrium concentration expressions. So they're in the overall equation, but I sort of shaded them out lightly because they're not going to be part of our process. So we need to get the initial amount of hydrogen gas. We have 10 grams, but we want moles or molarity. So the first thing we're going to do is convert this to moles. Once we have moles, we'll divide by 25 to get molarity. This problem you actually could push through in moles, although I don't think it will be helpful here. Actually, you could do it either way. It doesn't really matter. You could do it all in moles, but some of the kids get confused. If the delta N of the gas is 0, you can use moles instead of molarity. I tend to use moles if the problem asks for moles at the end, or grams. Otherwise, I'll usually just leave it as is. So we've got 10 divided by 2.016, and then
Can you not round it to 2 to make it 5?
yeah, you could if it was in your hand. It probably would be easier. So you have 0.198 molar. And then we also want to work it off this. We have 1 mole of hydrogen sulfide to grams of hydrogen sulfide, and we'll divide that by 25 liters as well. And just make sure that goes on the equilibrium line. And now what? How do you know the reaction must go in the forward direction?
Because you have
Because you don't have any product. So this would be plus 3x, correct?
Yeah.
And this would be minus 3x. So how do you figure out what x is?
divide that by 3.
Right, so you have 0.0852 divided by 3. So x is 0.0284. And if you multiply that by 3 and then subtract it from 0.198, you get this piece. How we doing? So far so good? And it looks awful, but if you take it slow, it's very digestible.
Are you getting x by subtracting 1 minus the initial concentration of the gas? I don't understand where you're getting x from.
X? How I solve for x here?
The value for x.
Okay, so this is 0 plus 3x is equal to that. So to solve for x, I just did this over 3. Because I know that E is equal to I plus C. So this plus this has to be equal to this.
Oh.
And then I just solve for the x.
And then when you solve for that x, you can solve for the x on the other side of the reaction.
Right, and once I knew what x is, I just plugged it in, multiplied by 3, and did this minus the product of that. Yes? Okay, so Kc here is hydrogen sulfide to the third over hydrogen gas to the third, and that's going to be 0.0 right here. Don't pick the wrong one. Make sure you're careful here. You may want to circle them off so you don't do anything silly. Now the threes, you don't just say, oh, the threes cancel. Be careful with stuff like that. You don't have the same variable there. So KC here is 0.429, and y in this case is that equal to KP as well? Because of the gases. So the delta N of the gas is 0. You have stoichiometric coefficients here of 3, and that's all you've got for the gases.
What if they weren't the same?
Then they wouldn't be equal. Then you'd have to do Kp is equal to Kc RT delta N of the gas. But because delta N of the gas is 0 here, RT to the 0 would be 1, so you don't have to deal with that term. All right, that's the basic framework, and we're just going to keep working it. Right now, we don't have any products, so you know you're going forward, so you know you're taking away from reactants and adding to the product side. Soon what's going to happen is you may have everything initially, and you need to figure out whether the forward or reverse reaction is favored by calculating Q, comparing it to a Kc, and then making a prediction. All right, we have a whole bunch of these to just lay out and do, and interpret. It won't be bad, I promise. Okay, the only thing now is that here we were given concentrations, either initial, equilibrium, we could figure out the other pieces, and we were calculating Kc. Well, you could be given Kc and have to find pieces and work it all through backward. But it's really the same process. It says calculating quantities from Kc and Kp values. Here you'll start with your initial reactants and no product. So again, you have to be going forward, and you'll be provided with a Kc value. You're going to use the X to identify the changes. I already introduced that. I like to do it from the beginning. And again, the coefficient is relevant. If the coefficient's 1, you'll subtract 1x or add 1x. If the coefficient's 4, you'll subtract 4x or add 4x, depending on which reaction, the forward or reverse, is favored. It says, consider the following reaction. You're generating hydrogen iodide from hydrogen gas and iodine. The Kc is 54.3 at the specified temperature. It says begin with 0.5 moles of hydrogen gas and 0.5 moles of iodine. And the fact that these are both the same makes life simpler. This is something you could be assessed. The volume is provided as well. We want to know how many moles of each gas will be present at equilibrium. Now this is a case where you're given moles, you're asked for moles, and the delta N of the gas is what? 0. If you're given moles and asked for moles and the delta N of the gas is 0, you can do the whole thing in moles. Okay? Because the volume unit will be treated the same way and it will cancel. Begin with, those are initial amounts of reactants shown right here in the I line. The fact that product is at 0 means which reaction is favored, forward or reverse? Forward. You have to move toward the area that you have nothing of. Otherwise, you can't have less than 0 for an amount. Why did I subtract 1x from each of these? Because it's the coefficient is 1 and you know you're going in which direction? Forward. And that's why we add. But look, I added 2x here. I made a mistake? No. You got the coefficient right there and you add it because that's the direction that is favored. So now you subtract because you know that E is equal to I plus C. So this plus negative x, same thing here, and 2x. And now it looks like you have x's all over the place and you're not going to be able to solve for anything, but that's not true. Shown right here is your KC expression. Products on top, so you have 2x in parentheses squared, because 2x in parentheses squared is equal to 4x squared. If you just write 2x squared, that's 2x squared, so be careful there. The KC was given, and each of these go in the denominator of the fraction. Now you want to solve for x. In this type of mathematical equation, the easiest way to solve for it is to take the square root of both sides, because if you take the square root of 4x squared, you get 2x. And here you basically have 0.5 minus x, parenthesed off, squared. So you take the square root of that, and you just get 0.5 minus x. Does that step make sense?
Yes.
Don't forget to take the square root of the other side too. That's the most common error I see kids making. At this point, you can cross multiply, solve for x, multiply it by 2 to get the equilibrium moles of hydrogen iodide, subtract it from each of these to get the equilibrium moles of each reactant. So let's take one from nothing and let's make it work. And we'll work through this very, very slowly, and that's pretty much as hard as it's going to get, because the other part of it, which I will show you, is not, if you need a graphing calculator or the quadratic equation to solve, it won't be on the AP exam. Okay, but it's something you certainly will be asked in college. It says, consider the reaction shown here. Begin with 1 mole each of the reactants in a 5-liter flask at 600 Kelvin. We want to know how many moles of hydrogen gas at equilibrium. We want to know the partial pressure of hydrogen gas at equilibrium. What approach do we use? What do we call that? Rice. And what goes in the R line? The equilibrium. And everything's a gas, so I'm not going to write gas. Now, is delta N of the gas 0? Yes. So we can do the problem in moles. And since moles are given and moles are asked for, let's do it. It says begin with. Where does 0.100 mole go? In the initial, right? And water? Same thing? Do we have any product? Nope.
If they don't tell you, just assume it's none.
What are we going to subtract from each of the reactants?
X1.
And what are we going to add to each of the products?
X.
What else do they tell us?
It's a 5-liter flask.
That we don't need. They don't tell us anything else. So it's 0.100 minus x, 0.100 minus x, and x. Is the E line clear? Does that make sense?
Yes. Equals I plus
Okay. What's my KC expression?
23.2.
No, not what it's equal to. What's the expression?
CO2,
CO2,
H2,
H2,
CO,
CO, H2O. Okay. And we do know that that is equal to 23.2. Now we're ready to plug and solve. We've got x squared in the numerator over 0.100 minus x squared in the denominator. And how can we solve this? So we have x over 0.100 minus x is equal to the square root, has to be about 4 point something, 4.82. Right? I think I copied it wrong. I missed a 0. As soon as I put it there, I was like, that can't be right, because you can't get more than what you started with, right? So I did it right in my calculator, like a ding-dong. I wrote it wrong, but that's something you want to make sure. Look at your answer. Does it make sense? That's not a mistake you want to make. All right. What did they ask for? Moles of hydrogen gas? So that's easy. That's what we got. If they had asked for moles of water at equilibrium, what would you do? You'd subtract that from 0.1. So you'd do 0.1 minus that, right? Okay. It also asks for the partial pressure of hydrogen gas at equilibrium. How would you do that? How do you solve for pressure? You have moles, you have R, you have T. It's easy as it sounds, guys. PV equals nRT, right? So you just do moles so you have 0.0828 moles. Your R, I'm going to plug that in higher. The temperature is 600 Kelvin. The volume is 5 liters. And that would be 0.0821 liters atmosphere mole Kelvin.
Does it have to be ATM or?
Could be anything. If they don't specify, it's usually ATM. What if they asked for the total pressure exerted by all the gases at equilibrium?
Find the partial pressure of the other gases.
You could find the partial pressure of all of them and add them all. That'd be too much work. You would put the total moles in, right? Okay, so those are all things that link back to the gas chapter. It's not that bad. It requires practice. Kids are usually good at it. All right. So far, we've been very fortunate in that we've always started with the same amount of moles of substance, which made it extremely easy to take the square root of both sides. Sometimes you don't get that lucky. I'm going to show you this one. You're not going to be asked to do this. I just want you to see it and really show you what you can do in your calculator instead of doing the quadratic. You may already be aware of it. Sometimes initial amounts are not the same. That requires the quadratic, or if you have a graphing calculator, a much easier approach. Same reaction, but the initial amounts now, highlighted in yellow in the rice table, are not the same. Same approach, subtract from the left, add 2x to the right because you're generating it and the stoichiometric coefficient is 2. You're going to put 2x parenthesis to the second power in the numerator for products, each of these in the denominator, and now you can't take the square root of both sides. So what you need to do here is you need to either somewhat solve it, or you can just put it in your calculator as is. Let me show you. Before I plug it in, I just want you to see the derivation. Let's make sure. So I've got 4x squared is equal to 54.3 times 0.800 minus x times 0.500 minus x, correct?
Mm-hmm.
And if I move this to the other side, I can just do this, and this is 0, correct? Okay, let's see if it works. My calculator is slightly different than yours. I'll try and talk you through yours if I can figure yours out. But I'll show you. Mine has a solver button. I think for some of you it's in the math functionality. Okay, so my equation I'm going to type in is 54.3 open parentheses 0.8 minus x close open 0.5 minus x close minus 4x squared equals. My exp is going to be 0, and the x is what I'm going to solve, and it takes a minute to crank it out, and my x is 0.456. So my x is 0.456, and now if you go back to this page and we focus on the hydrogen gas right here, 0.8 minus 0.456 is 0.344 moles of hydrogen gas, which is what you see in blue on the page. Similarly, 0.5 minus 0.456 will be 0.044 moles of iodine, shown in blue. And here, if you plug the x in, multiply by 2, and then square it, you get the following. So years ago, you used to have to sit there with quadratics and stuff. And even though I don't like technology sometimes because you guys get carried away with it, in this case, I think it's a very, very good thing, because you could do a problem in 3 seconds as opposed to one whole sheet of paper and then be like, am I right? So it's very easy. Some of the calculators gave 2 x values. Mine always gives the right one. I'm not sure why. If you get a value that's greater than what you started with, it's not the right one. So it's an interesting thing. I just wanted to show you. It says the solving piece is too extensive for the AP exam, so they won't ask you it, so don't sweat it. I tried to get rid of those problems in the homework. If I didn't get rid of them, I'll take a second look and make sure that I do, so that you don't stress over it. The other problem I canceled. We do want to look at number 4, and then we'll give the very last piece a try, because this is the only other thing they can do to you. But I think all they're going to ask you to do is figure out which reaction is favored and why. And this I'm seeing all over the exam, so this is the Q aspect of it. And again, I don't think you're going to have to set it all up. So this will just link us back to Q, and it'll be very good for you. So we just want to do maybe 2 more problems, and then you'll be able to practice. How we doing?
Does it, that calculator's thing work at all with this?
No.
Just the,
No. But they won't ask you it, so don't worry about it. If you have them, it's kind of fun to try it out. And I would think it's something like, might you use that solver button in math, right? In any of your math classes? No? Well, even if you had a quadratic in Algebra 2, you should be able to process it that way. It would go much
but
faster.
you have to use these types of calculators.
Oh, well,
So
then you can't.
do it.
And then, like, in calculus, is the whole test calculator free now? But maybe it's not the same stuff. I took calculus back in 19-something, so actually I know when I took it, but you don't need to know that. We did have calculators back then, but not graphing ones. So we had to do stuff in our head. That's why I know what the square root of 2 is, and you don't.
1.1.
Nope.
1.1.
1.414. All right, so that's the fun little calculator game. This is more interpretational once you get Q. This is very simplistic. This is very much in the POGIL packet. So we'll go through these, and then we'll be able to do a lot of practice, which is exactly what the doctor ordered after this chapter. So it says, consider the following reaction. You're generating phosgene from carbon monoxide and chlorine gas. The Kc is given. It says, what will be the amount of each substance when equilibrium is established in a reaction mixture that initially has 0.0100 moles of carbon monoxide, 0.0100 moles of chlorine gas, and 0.1 moles of phosgene. Instead of the question reading that way, I think what you're going to be more apt to see, and this really is going to link into our solubility equilibria a little later on, so it'll be a good push in that direction. The type of question that you might see would simply be, would the forward or reverse reaction be favored justify your choice? And this could be in part 1 or part 2. If it were in part 1, the numbers would be really easy. But even these numbers that look miserable are really pretty easy if you deal with scientific notation, which I'll show you. All of a sudden, for the first time, we're given initial amounts of everything. So it's not obvious if the forward or reverse direction is favored. And it's not always, oh, this number's bigger than this. Don't do that. The way that you figure this out is you calculate what?
Okay.
What comes from initial amounts?
Oh,
Q. Q, Q. And this is why the Pogel packet's going to be good for you. So Q is just product, initial amount over reactants. Why not? They give it to you in molarity, making life easy, because the delta N of the gas is not 0 here. I have 0.01, 0.00100, and that's squared because it's the same for both, correct? Okay, now some of you look at this and you're going to sit there and start dividing longhand. Please don't do that. This is, and I'm going to make it easy, getting rid of all these zeros, is 1 times 10 to the negative 2. This is 1 times 10 to the negative 3 squared, right? So far, so good? Okay, so that is 1 times 10 to the negative 2, 1 times 10 to the negative 6 is 1 times 10 to the 4th, minus 2 minus negative 6, all right? That is 7th grade math. Got to be able to do adding and subtracting of negative numbers in your head. My daughter hates me because I make her do them every night.
Yeah.
Too bad. So that's Q. K is given at 1.2 times 10 to the 3rd. Which is bigger? Q, right? So if Q is greater than K, the reverse reaction is favored. In an effort to establish equilibrium. There was a specific, that's all you're really going to need though. There's a specific way I wrote it in the Pogel packet, and you'll look at that, or I'll pull it in a couple seconds. If you go back and look at my grid, did the math make sense? Slow and steady, right? If you look at my grid here, you can see that I subtracted from the reverse, from the, I gave it away. You can see that I subtracted from the product side because the reverse reaction was favored. Again, you're not going to be asked to solve for all the pieces, so you just want to be able to solve for Q and interpret it. So this one too, we'll give it a shot. And the only difference on the last problem is it deals more with pressure than concentration, so we'll take a look at it. How would we set up this one? Actually, this one is, let's simplify this. It says how many moles of each reactant and product Who cares? Look what they give you here. What do they not give you initially? Iodine. So the reaction must run in reverse. Okay? And you couldn't figure out a Q. We're not going to do that one. Let's look at 5. I would like to at least address this one. This we should be able to approach at all levels. Okay. It says a sample of phosgene is introduced into a constant volume vessel at 395 and observed to exert an initial pressure of 0.351 atmospheres. So that's the initial pressure of phosgene. When equilibrium is established, what will be the partial pressure of each gas and the total pressure? Let's see if we can do this one. Oh, we can do it. Wine, wine, wine. I want to do a pressure one because sometimes they give you pressure and I don't want it. You'd work it the same way, but for some of you, if I change one word, it's so bothersome to you that even though you know how to do it, you start to sink. So we don't want any sinkies. All right. It exerts an initial pressure. So why am I putting this right here? That's the initial pressure of that substance. What are the initials of these? Nothing. So I have to take away, add, and now the Kp is going to be the partial pressure of phosgene over the partial pressures of each of these. And you would need quadratic here. You'd have to plug it in, so we'll stop there. What I wanted you to see in this problem is how did you know the reaction had to run in reverse? You didn't have any reactant. What I'm a little sorry about, but this is where you're going to get it in the POGL packet, and I can pick specific ones now or you really have a lot of time to work on it. This concept has become critically important. I'll try and add another problem into my notes, but this aspect is what the POGL packet is all about, and I think that will help you greatly. The chapter can be a bit overwhelming. A lot of the really hard stuff is no longer assessed, but you have to be able to interpret and explain, and that is critical here. You must know Le Chatelier's principle inside and out. It is so very simple. You can be so successful on these types of questions. Please do some of the practice problems. If you want me to pull some more out now, we can. You've got quite a bit of time to practice, which is good because also so many kids are out today. I ask that you please get well over the weekend because you're all sick and read the lab over. It is an inquiry-based lab. It's the one that says Le Chatelier's principle. I can try and pull it up on Edline now so you can see where it is. It's not 3.2. It's not the Beer's Law lab. It's the one that says Le Chatelier's principle. That's coming too. Try and read it over before you come in. That's what we'll work on. We also can address any issues, concerns that you have. Your quiz, I believe, is slated for Friday. So again, you're coming up early. They're getting the weekend, but you have the weekend. You have everything now that you need. Please work on the POGL packet here, all right? I'm going to post one AP Insight quiz. Actually, I believe I unlocked it already. It'll be very good for you. Keep in mind what happened last time for those of you who didn't do it. I think you learned your lesson. I'm sorry. It's your fault though. Questions?